Something is falling toward our sun. It came from the direction of the constellation Lepus, traveling at a velocity that makes return impossible. 42 kilometers per second relative to our star. A speed that means it will pass through our solar system once, and then continue outward into the dark between galaxies, never to return. The Discovery team at the Atlas survey in Hawaii detected it first. They followed protocol. They measured its brightness. They calculated its orbit. They checked their work twice. And then they made an announcement. They called it a comet. The designation is 3I/Atlas. The I stands for interstellar. Only the third confirmed object in human history to enter our solar system from another star system entirely. The first was Oumuamua in 2017. The second was Borisov in 2019. Both of those objects sparked years of debate. Oumuamua, in particular, became famous for what it wasn't. It showed no coma, no tal, no outgassing visible to our instruments. The shape was wrong. Its acceleration was wrong. And when it left behind more questions than answers. Scientists hoped the third interstellar visitor would be different. They hoped 3I/Atlas would be simple. A comet, a ball of ice and rock from a distant solar system, behaving exactly the way comets should behave. Finally, after Oumuamua's strangeness, the universe would send us something normal, something explainable, something that fit neatly into our existing categories. That is not what happened. Within weeks of the initial detection, the data started arriving from observatories around the world. Spectral analysis, brightness curves, thermal emissions, trajectory measurements. Each dataset was supposed to confirm what everyone already believed. Instead, each dataset added another question. The brightness fluctuations didn't match known rotation models. The spectral signatures showed chemical combinations that shouldn't exist together. The trajectory showed acceleration that couldn't be explained by solar wind or outgassing. The thermal readings contradicted the size estimates. The coma developed on a timeline that made no physical sense. One anomaly could be instrument error. 2 anomalies could be unusual composition. 3 anomalies might indicate a rare but natural phenomenon. But the count didn't stop at 3. As of today, there are 11 documented anomalies associated with 3I/Atlas. 11 measurements that deviate from expected cometary behavior. 11 data points that individually might be dismissible, but together they form a pattern. And that pattern is why a growing number of astronomers have quietly stopped using the word comet. Not publicly, not in press releases, but in private communications, in conference hallways, in the margins of draft papers awaiting peer review. A different kind of conversation is happening. A careful conversation. A hesitant conversation. A conversation about what we might actually be looking at. By the end of this video, you will see all 11 anomalies. You will understand why each one matters. You will hear the strongest argument for natural explanation, and you will see exactly where that argument breaks down. You will watch the data accumulate, and you will understand why the question is no longer whether 3I/Atlas is unusual. The question is what kind of unusual we're dealing with. Stay until the end, because the 11th anomaly is the one that changes everything. And you need to see anomalies 1 through 10 before that final piece makes sense. Now prepare yourself. We begin part 1. Before we examine what's wrong with 3I/Atlas, we need to establish what right looks like. We need to understand comets. A comet, at its simplest, is a frozen traveler. A mixture of ice, dust, and rock, formed in the cold outer regions of a solar system, where temperatures stay low enough for volatile compounds to remain solid. Water ice, carbon dioxide ice, methane, ammonia. These substances, mixed with silicate dust and organic molecules, compressed together over millions of years into objects ranging from a few hundred meters to several kilometers across. When a comet remains far from its star, it stays dormant, a dark, quiet body drifting through the void. But when its orbit brings it closer to stellar heat, something changes. The ices begin to sublimate. They transform directly from solid to gas, skipping the liquid phase entirely. This outgassing creates a cloud of material around the nucleus called a coma. Solar radiation and stellar wind then push this material outward, forming the famous tail that ancient humans watched with fear and wonder. This process is predictable. We have observed thousands of comets in our own solar system. We understand the physics. We can model the behavior. When a comet approaches the sun, we can calculate when outgassing should begin based on its distance. We can predict how bright it should become based on its size. We can estimate its rotation based on how its brightness fluctuates over time. Comets follow rules. These rules are not arbitrary. They emerge from fundamental physics. The relationship between solar heating and sublimation rates. The connection between nucleus size and gravitational binding. The correlation between composition and spectral signatures. When astronomers first detected 3I/Atlas, they applied these rules. They measured its incoming velocity and confirmed its interstellar origin. They observed initial brightness and estimated its size. They detected early signs of outgassing and declared it a comet. The logic was sound. The methodology was correct. Every step followed established protocol. But here is what you need to understand about scientific classification. Classification is based on pattern matching. We observe a new object. We compare its properties to known categories. If the properties match, we assign the label. This system works extraordinarily well when objects behave normally. The system struggles when objects don't. Oumuamua was the first warning. When it passed through in 2017, it matched no known category cleanly. Its extreme elongation was unprecedented. Its lack of visible outgassing despite acceleration suggested something pushing it that we couldn't see. Some scientists proposed exotic natural explanations. Others whispered about artificial origin. The debate never fully resolved because Oumuamua left our observable range before we could gather enough data. Borisov in 2019 was a relief. It looked like a comet. It behaved like a comet. It had a coma, a tail, the expected spectral signatures. Scientists breathed easier. Interstellar objects could be normal after all. 3I/Atlas was supposed to continue that trend. The initial observations supported optimism. There was outgassing. There was a developing coma. The word comet appeared in the first official communications, and nobody questioned it. But data continued arriving, and the pattern began to break. The first anomaly was subtle, a fluctuation in brightness that didn't quite fit standard rotation models. Easy to dismiss, probably instrument noise, probably atmospheric interference. Then came the second anomaly, and the third, and the fourth, each one individually explainable, each one probably nothing, but they kept coming. And now we need to look at them, one by one, in order, because the sequence matters. The sequence reveals something that the individual data points hide. But that's not the strangest part. The strangest part is how long it took anyone to start connecting them. There are 11 documented anomalies we need to walk through. I will show you each one, not with speculation, not with sensationalism, just the data, what was observed, what was expected, and where the gap appears. By the time we reach anomaly 11, you will understand why some astronomers have gone quiet. Why certain emails between research teams have become shorter. Why the word comet now appears in quotation marks in internal communications. But we start at the beginning. Anomaly number 1. The brightness curve. When a comet rotates, its brightness changes. Different surfaces reflect light differently. Rocky areas appear darker. Icy patches appear brighter. By measuring these fluctuations over time, astronomers can determine rotation rate. They can model the object's shape. They can predict future brightness variations. 3I/Atlas showed fluctuations. That was expected. What wasn't expected was the pattern. The brightness curve didn't match any known rotation model. Not spherical. Not elongated. Not tumbling. The variations seemed almost random at first. Then someone noticed they weren't random at all. They followed a pattern. But a pattern that implied a shape inconsistent with gravitational physics. A natural body of that size should have collapsed into a more regular form millions of years ago. The brightness curve suggested it hadn't. Probably unusual composition. Probably an exotic structure we haven't encountered before. Probably explainable. Move on. Anomaly number 2. Spectral signatures. When light passes through a comet's coma, certain wavelengths get absorbed. Different molecules absorb different wavelengths. By analyzing which wavelengths are missing, astronomers identify what the comet is made of. Water, carbon monoxide, cyanide, familiar compounds with familiar signatures. 3I/Atlas showed absorption lines. That was expected. What wasn't expected was the combination. The spectral analysis revealed materials that don't typically form together. Compounds that require different temperature ranges to solidify. Substances that should have separated during formation, not bonded. One researcher described it as finding ice endite burning coal frozen together at molecular scale. Not impossible, but requiring conditions that shouldn't exist naturally. Probably a unique formation environment. Probably a solar system unlike anything we've modeled. Probably explainable. Move on. Anomaly number 3. Trajectory deviation. Comets don't travel in perfect gravitational arcs. When they outgas, the escaping material creates thrust. This push is called non-gravitational acceleration. We account for it in every cometary orbit calculation. 3I/Atlas showed non-gravitational acceleration. That was expected. What wasn't expected was the magnitude. The trajectory deviation exceeded what the visible outgassing could produce. By a significant margin. The object was being pushed by something. But the push was stronger than the exhaust. This happened with Oumuamua too. That's what sparked the artificial origin hypothesis. With Oumuamua, there was no visible outgassing at all to explain the acceleration. With 3I/Atlas, there was outgassing. But not enough. Probably hidden jets on the dark side. Probably asymmetric sublimation we couldn't observe. Probably explainable. Move on. Anomaly number 4. Rotation rate. I mentioned the brightness curve suggested an unusual shape. But there's another problem. The implied rotation rate is too fast. For an icy body of the estimated size, spinning at that speed should cause structural failure. The centrifugal force should exceed the tensile strength of ice. The object should tear itself apart. It hasn't. This means either our size estimates are wrong, our composition assumptions are wrong, or the object has structural integrity that ice alone cannot provide. Probably a denser core than expected. Probably iron-nickel beneath the surface. Probably explainable. For anomalies, each one dismissible. Each one probably natural. Each one with a reasonable alternative explanation. But keep that word in mind. Probably. Because the next 5 anomalies make probably harder to say. That was anomaly number 4. And we haven't even reached the data that made astronomers go quiet. Take a slow breath. We have covered 4 anomalies. Each one unusual. each one potentially explainable in isolation. Now we enter the territory where explanations require more effort, where the word probably starts carrying more weight than it should. Anomaly number 5. Thermal emission. Every object radiates heat. The amount depends on two factors: how much solar energy it absorbs, and how efficiently it releases that energy back into space. For a comet of known size and distance from the Sun, thermal emission can be predicted with reasonable accuracy. 3I/Atlas emits heat. That was expected. What wasn't expected was the mismatch. The thermal signature suggests an object significantly smaller than brightness estimates indicate, or significantly larger. The two measurements contradict each other. If the brightness is correct, the thermal emission is wrong. If the thermal emission is correct, the brightness is wrong. Both measurements have been verified. Both instruments are functioning normally. The data is clean. It simply doesn't agree with itself. Probably unusual surface properties. Probably reflectivity variations we haven't accounted for. Move on. Anomaly number 6. Coma development timeline. As a comet approaches the Sun, its coma grows. The timeline follows predictable physics. Distance determines solar heating. Heating determines sublimation rate. Sublimation rate determines coma density. 3I/Atlas developed a coma. That was expected. What wasn't expected was the timing. The coma appeared earlier than distance calculations predicted. Then it stabilized. Then it grew again at a rate inconsistent with the first growth phase. The development wasn't gradual. It was stepped, almost staged. Natural comets don't do this. Their coma development follows smooth curves based on continuous heating. 3I/Atlas behaved as if something was controlling the rate, turning it up, turning it down, adjusting, probably internal structure variations, probably pockets of volatile material releasing at different depths. Move on. Anomaly number 7. Dust-to-gas ratio. When comets outgas, they release both gas and dust. The ratio between these components tells us about internal composition. Our solar system's comets have established ranges, different families, different origins, but all within expected parameters. 3I/Atlas releases gas and dust. That was expected. What wasn't expected was the ratio. It falls outside every observed range. Not slightly outside, dramatically outside. The object releases far more gas relative to dust than any comet we have recorded. This could indicate ice purity beyond anything we've encountered. Water ice with almost no rocky contamination. The cleanest frozen material ever observed. Or it could indicate something else entirely. Probably exotic formation conditions. Probably a stellar system with unusual chemistry. Move on. Anomaly number 8. Size and mass discrepancy. We estimate cometary mass through gravitational effects and outgassing dynamics. We estimate size through brightness and thermal measurements. These estimates should converge. For 3I/Atlas, they diverge. The mass estimate suggests a dense, compact body. The size estimate suggests something larger and more diffuse. The two cannot both be correct for a natural object with uniform composition. Something about its structure defies consistent measurement. Probably density variations. Probably a rubble pile configuration. Move on. Anomaly number 9. Solar heating response. As comets approach the Sun, their activity increases proportionally. Closer means hotter. Hotter means more sublimation. More sublimation means more visible activity. 3I/Atlas responds to solar heating. That was expected. What wasn't expected was the curve. Activity doesn't track distance linearly. There are plateaus where nothing changes despite increasing heat. There are spikes where activity surges without corresponding distance change. The object seems to respond to something other than simple thermal input. 9 anomalies documented. Each one has been reported. Each one has been verified. Each one has been assigned a tentative natural explanation by cautious scientists following proper protocol. But here is what you need to understand. In March 2026, when 3I/Atlas reaches perihelion, these readings will either stabilize into a pattern we recognize, or they will continue diverging, and divergence has implications. But the 10th anomaly is the one that changes the conversation entirely. Now we need to stop. We need to be fair. I have shown you 9 anomalies, each one framed as unusual, each one presented as a deviation from expectations. But science doesn't work by accumulating mysteries and declaring something unexplainable. Science works by testing the simplest explanation first. And the simplest explanation for 3I/Atlas remains natural origin. An interstellar comet. Strange, yes. Unusual, certainly. But still a comet. Still a frozen body from another star system behaving according to physics we understand. This is the skeptic's position, and it deserves serious consideration. The argument goes like this. We have observed comets in our solar system for centuries. But our solar system is one example. One set of formation conditions. One stellar environment. One chemical history. 3I/Atlas comes from somewhere else. We don't know which star system. We don't know what conditions existed there. We don't know what raw materials were available. We don't know what temperatures, pressures, or radiation environments shaped its formation. Given complete ignorance of origin conditions, shouldn't we expect unfamiliar properties? The skeptic says yes. Consider anomaly 1, the strange brightness curve. Perhaps 3I/Atlas formed in a debris disk with unusual gravitational dynamics. Perhaps collisions shaped it differently than objects in our system. Unusual shape doesn't require unusual explanation. It requires unusual history. Consider anomaly 2, the spectral signatures that shouldn't coexist. Perhaps the parent star system had different elemental abundances. Perhaps heavy metals were more common. Perhaps organic chemistry followed different pathways. Unusual chemistry doesn't require unusual explanation. It requires unusual environment. Consider anomaly 3, the excess acceleration. Perhaps the outgassing is happening from vents we cannot observe. Perhaps the jets are pointed away from Earth at angles that hide their true magnitude. Unusual thrust doesn't require unusual explanation. It requires unusual geometry. The skeptic continues through each anomaly. Thermal emission mismatch. Unusual surface texture. Coma development staging. Unusual internal structure. Dust-to-gas ratio. Unusual purity. Size-mass discrepancy. Unusual density distribution. Solar heating response.
Unusual composition layée.
For every anomaly, there exists a natural explanation. Not a proven explanation, but a possible one, a reasonable one, an explanation that doesn't require abandoning everything we know about physics and chemistry. This is powerful. This is how science should work. Extraordinary claims require extraordinary evidence. And claiming that 3I/Atlas is anything other than a comet is an extraordinary claim. The burden of proof lies with those making that claim. The skeptics are right to demand more. But here is where the defense encounters difficulty. Each individual anomaly can be explained naturally. That's true. But the explanations don't connect. The unusual shape requires one set of formation conditions. The unusual chemistry requires a different set. The unusual outgassing geometry requires another. Each explanation works in isolation. but they don't form a coherent picture. For 3I/Atlas to be a natural comet, it needs to have formed in an environment that simultaneously produced extreme elongation, exotic chemical bonding, hidden jet configurations, impossible rotation stability, contradictory thermal properties, staged coma development, unprecedented gas purity, internal density inversions, and nonlinear heating response. That's not one unusual comet. That's 9 unusual comets compressed into a single object. And this is before we reach anomaly 10. Anomaly number 10. Outgassing vector alignment. When comets release gas, the jets point in directions determined by where sunlight hits the surface. Hot spots create vents. Vents create jets. Jets point away from heat. 3I/Atlas has jets. We can see them. They don't point away from the sun. They point in directions that have no thermal justification, as if the outgassing is being directed, controlled, and the skeptical explanation for this requires invoking subsurface channels that somehow redirect gas flow against basic fluid dynamics. It requires physics we have never observed in any comet. Ever. There is one more anomaly, number 11, and when you see it clearly, you'll understand why some astronomers have stopped using the word comet altogether. Anomaly number 11. The coherence pattern. This is not a single measurement. This is not one instrument reading. This is what emerges when you stop looking at individual data points and start looking at relationships between them. Someone did this 6 months after discovery. A graduate student working on trajectory refinement. She wasn't looking for patterns. She was debugging a calculation error. But she found something. The anomalies correlate. When the brightness curve deviates most strongly, the thermal emission mismatch peaks. When outgassing vectors shift, rotation rate fluctuations follow. When coma development stages, spectral signatures change simultaneously. These correlations shouldn't exist. In a natural comet, each property is governed by independent physical processes. Shape doesn't affect chemistry. Chemistry doesn't affect thermal emission. Thermal emission doesn't coordinate with outgassing direction. But in 3I/Atlas, they move together, as if connected, as if controlled by the same underlying mechanism. The graduate student showed her advisor. Her advisor asked her to verify. She verified. He asked her to verify again. She did. The correlations held. The paper was never published. Not because it was wrong, because no one knew what to say about it. Now we enter speculation territory. I will be clear about what is fact and what is hypothesis. I will label everything. You deserve to know where the data ends and interpretation begins. Hypothesis A. The most normal explanation. 3I/Atlas is an extremely rare primordial object. A relic from the earliest era of its home star system, before planets formed, before gravitational sorting separated materials. A frozen time capsule preserving conditions we have never encountered. The correlations exist because primordial material has internal dependencies we don't understand. Properties we've never measured because such objects don't survive in mature solar systems. We're seeing something ancient, something unusual, but still something natural. This hypothesis is possible. Hypothesis B. Stranger. 3I/Atlas is a fragment of a planetary core. Somewhere in another star system, a planet was destroyed. Collision.
Stellar explosion.
Gravitational disruption. The core shattered. A piece was ejected at interstellar velocity. Planetary cores have unified structure. Internal layers that form together under extreme pressure. Properties that correlate because they emerged from the same differentiation process. We would be looking at the remains of a dead world. This hypothesis is possible. Hypothesis C. The most unsettling possibility. The correlations exist because they were designed to exist. The properties coordinate because coordination was intended. The measurements contradict our models because our models assume natural origin. The object doesn't behave like a comet because it was never a comet. I will be direct. Some characteristics of 3I/Atlas fall within parameters that theoretical papers have outlined for artificial construction. Not proof of artificial origin. Not evidence that would satisfy a scientist demanding certainty. But consistency, compatibility. The rotation rate suggests structural integrity beyond ice. The outgassing vectors suggest directed thrust rather than passive sublimation. The thermal signature suggests surface properties optimized for something other than random cosmic formation. And the correlations suggest systems working together. I am not telling you this is true. I am telling you this hypothesis exists. I am telling you that serious people have considered it. I am telling you that the reason certain astronomers have gone quiet is not because they believe this explanation. It's because they cannot eliminate it. By late 2026, during closest approach, spectroscopic analysis at full resolution will either reveal the chemical fingerprints of a natural body from another star system, or it will show us something our classification systems were never built to describe. Take a slow breath. Let's zoom out for a moment. What do we actually know versus what we're inferring? We know 11 anomalies exist. We know they correlate. We know no natural explanation accounts for all of them coherently. We don't know what 3I/Atlas is. But the question isn't whether it's strange. The question is whether we're prepared for what strange might mean. We are not powerless here. The universe has sent us a question, but it has also given us time to answer it. 3I/Atlas is still approaching, still observable, still within range of our instruments. What happens over the next 18 months will determine everything. Let me tell you exactly what astronomers are watching for. And let me tell you what each result would mean. First,
Perihelion passage.
in March 2026, 3I/Atlas will reach its closest point to our Sun. Maximum solar heating. Maximum stress on whatever structure holds it together. Maximum outgassing activity. If the object is a natural comet, perihelion will be violent. We should see fragmentation. We should see massive coma expansion. We should see behavior consistent with an icy body being torn apart by thermal stress. If the object is something else, perihelion will be different. The structure will hold. The outgassing will remain controlled. The correlations between anomalies will either strengthen or reveal new patterns we haven't detected yet. Watch March 2026. Second, spectroscopic deep scan. Multiple observatories have allocated time for high-resolution spectral analysis during closest approach. This isn't the preliminary scan from Discovery. This is detailed chemical fingerprinting at wavelength resolutions we couldn't achieve at initial distance. If 3I/Atlas is natural, we should find isotope ratios consistent with stellar nucleosynthesis. We should find molecular signatures that match known astrophysical processes. We should find chemistry that, however unusual, fits within the periodic table as we understand it. If the spectral analysis returns anomalies within the anomalies, that changes everything. Certain isotope ratios don't occur naturally. Certain molecular structures require manufacturing. Certain chemical combinations only exist through deliberate synthesis. The data will speak. Third, the James Webb Space Telescope. Dedicated observation time has been allocated. The most powerful space telescope ever built will turn its instruments toward 3I/Atlas during the optimal observation window. Webb can see thermal signatures in extraordinary detail. Webb can detect atmospheric composition around objects with precision no ground telescope can match. Webb can measure properties that remain invisible to every other instrument we possess. Those results will be processed. They will be reviewed. They will be published. And when they are, the conversation we're having tonight will either become a footnote in cometary science, or the beginning of something else entirely. Now watch what happens when we connect three facts. Fact 1. The correlations between anomalies suggest unified causation. Something connects these properties. Fact 2. Perihelion will stress that unity. Whatever holds 3I/Atlas together will be tested by maximum solar exposure. Fact 3. We will be watching with the most sensitive instruments ever built. This is not a mystery that will remain unsolved. This is not ambiguity that will persist forever. We have the tools. We have the observation window. We have the attention of every major astronomical institution on Earth. The answer is coming. But here is what you need to understand about the timeline. Science moves slowly. Data collection takes months. Analysis takes more months. Peer review takes more still. Publication happens only after multiple verification rounds. The observations will happen in 2026. The preliminary analysis might emerge in late 2026 or early 2027. The definitive papers might not appear until 2028. This means we are entering a period of waiting. A period where data exists but isn't public. A period where astronomers know things they cannot yet share. A period where silence might mean nothing. Where silence might mean everything. If X happens, we confirm natural origin. Unusual comet. Case closed. Science advances. If X doesn't happen, the questions multiply. And then different conversations begin. Conversations that have protocols. Conversations that involve more than astronomers. The data will arrive. The question is whether we'll recognize what it's telling us. And when you understand that, the silence from certain observatories starts to make more sense. Let the data settle now. Let the numbers quiet themselves. Let the anomalies rest in your mind without demanding immediate resolution. We have traveled through 11 documented peculiarities. We have examined the skeptic's defense and watched it strain under accumulated weight. We have considered 3 hypotheses and acknowledged that none can be eliminated. Now we step back, far back. Consider what it means that we can have this conversation at all. For most of human history, the stars were fixed.
Permanent.
Unchanging points of light in a ceiling we could not reach. Our ancestors watched comets with terror because they represented change in a cosmos they believed was eternal. Disruption in a system they thought was stable. We know better now. We know the stars move. We know the cosmos churns with violence and creation. We know that objects travel between solar systems on journeys lasting millions of years. We know that the space between stars is not empty but filled with wanderers. 3I/Atlas is one such wanderer. Whatever it is, it left its home system before humans existed. It traveled through darkness longer than our species has had language. It crossed distances so vast that light itself takes years to make the same journey. And now, in this brief window of cosmic time, its path intersects with ours. We get to look at it. We get to measure it. We get to ask what it is. This is remarkable. Not the anomalies. Not the mystery. The simple fact that we are here with telescopes pointed outward, catching visitors from other stars and wondering about their nature. 100 years ago, we couldn't have detected 3I/Atlas. 100 years from now, we might have answers we currently lack the technology to obtain. But right now, in this moment, we exist in the space between ignorance and knowledge. That space has a name. We call it curiosity. The history of astronomy is filled with objects we misclassified. Pulsars were first called LGM, for little green men, because their regular signals seemed too precise for nature. Quasars were called quasi-stellar objects because we couldn't determine what they actually were. Dark matter got its name from absence, from the holes in our understanding rather than the thing itself. Every unknown eventually becomes known. Every mystery eventually dissolves into either mundane explanation or revolutionary discovery. There is no third option. 3I/Atlas will not remain ambiguous forever. The universe doesn't work that way. Evidence accumulates. Instruments improve. Understanding deepens. The question is not whether we will learn the truth. The question is whether we are ready for it. If 3I/Atlas is a comet, we learn something beautiful about the diversity of interstellar chemistry. We expand our models. We publish papers. We move forward. If 3I/Atlas is something else, we face a different kind of learning. A kind that doesn't just add to our knowledge but restructures it. A kind that changes not just what we know but who we understand ourselves to be. Both outcomes have value. Both outcomes represent the universe answering a question we dared to ask. For now, the visitor continues its approach, falling toward our sun, carrying its secrets through vacuum and radiation and time. We watch, we measure, we wait, and perhaps tonight, as you drift toward sleep, you might consider the strangeness of this arrangement. Beings made of matter on a small planet, orbiting an ordinary star, pointing instruments at an object from impossibly far away and asking, with genuine hope of answering, "What are you?" That question travels outward at the speed of thought. The answer is already traveling toward us. All we need is patience. Close your eyes now if you wish. The stars will keep their appointments. And when the data arrives, we will face it together. Good night.